Hi, this video will be explaining to you the physics behind 3 jumps in figure skating, the Lutz, Axel, and loop. This is a double Lutz. A Lutz is a jump that takes off from a left, if you are right-handed, backward outside edge, and it is assisted by the right toe pick. Then you land on a right backward outside edge. Firstly, in order to understand any jump, you need to know about Newton's third law, action and reaction. Newton's third law states that when object A exerts a force on object B exerts an equal amount of force on object A, but in the opposite direction. This means that in the Lutz, by pushing down on the ice with your left leg, you can jump up. The toe pick is what allows you to start the rotation. Now, in order to understand more about rotation, you need to know about moment of inertia. Moment of inertia is how hard or easy it is for an object to rotate. The larger the moment of inertia, the harder it is to rotate. The moment of inertia can be defined by the following formula: I equals mr squared, where I is the moment of inertia, m is the mass of the object, and r is the distance from the mass to the rotating axis. The mass of the object, in this case a figure skater, is constant. The distance from the mass to the rotating axis, however, is not. When the arms and legs are spread, the effective distance, r, is larger, and so consequently the moment of inertia is also larger. When the arms and legs are closed, the moment of inertia is less, since the effective distance is less. Next, to properly understand rotation, you also need to know about angular momentum. Angular momentum can be defined by L equals I omega, where L is the angular momentum, I is the moment of inertia, and omega is the angular velocity. Angular velocity measures how fast an object rotates. Then, to understand more about rotation in a jump, you need to understand the law of angular momentum conservation. It states that angular momentum will be conserved when an object rotates. So that means that I1 omega 1 equals I2 omega 2. For example, when arms and legs are extended right before a jump, there is a large moment of inertia, which is I1, and there's a low angular velocity, which is omega 1. In the air, the arms and legs are tightened to reduce the moment of inertia, which is I2. According to the law of angular momentum conservation, the angular velocity of a skater in the air, which is omega 2, is equal to I1 over I2 times omega 1. Since I1 is more than I2, omega 2 will be more than omega 1. And so that's how angular velocity can be gained in a jump. As you may have noticed, arms and legs are extended for the landing. That's to reduce angular velocity so that you can have a nice landing. Finally, the last thing you need to know about the Lutz is how to generate rotation. In order to understand how that works, picture yourself on the edge of one of those rotating platforms from the playground. Now imagine your friend throws you something heavy, like a school bag full of books. The platform would start rotating, right? Well, that's pretty much how rotation is generated in a Lutz. The skater is like the school bag, and the toe pick is like the axis of rotation of the platform. The next jump we'll be discussing is the axle. This is an axle. In terms of physics, the only things that are different from the axle to the Lutz are how you get into the air and how rotation is generated. We'll start with how you get into the air. A big part of it is still Newton's third law, so your left leg pushes down on the ice and the ice pushes you up. The different part, however, is the added swing from your right leg, which the Lutz doesn't have. Now, in order to understand what that swing does, you need to understand the law of conservation of energy. This law states that the kinetic energy, the energy of motion, added with the potential energy, which is stored energy or the energy of position, is always equal to the total mechanical energy. To find the kinetic energy, you do 1/2 of the mass times the velocity squared, so EK equals 1/2 mv squared. Potential energy can be defined by the product of the mass, the acceleration due to gravity, and the height, so EP equals mgh. On the ice before a jump, there is no potential energy and a lot of kinetic energy. At the highest point of a jump, there is only potential energy and no kinetic energy. So, with the law of conservation of energy in mind, this means that the more kinetic energy you have when you're on the ice, the more potential energy you'll have when you're in the air. The more potential energy you have, the greater the height, since you cannot change your mass while skating, and you do stay on the same planet too. When the mass and the acceleration due to gravity are both constant, then the only way to increase the potential energy is if you increase the height. So now back to that swinging right leg. The faster you swing it, the higher your jump will be. So now that we've covered how the takeoff works, we can move on to how rotation is generated. The Axel isn't topic assisted, so in that sense it's different from the Lutz. Otherwise though, rotation is generated quite similarly between the two jumps. The school bag and rotating platform explanation still works, you've just switched things up a bit. The swinging right leg becomes like the school bag, and the left foot is the axis of rotation of the platform. That's all that's different about the Axel really in terms of physics. The rest is just what I explained earlier. Now we can move on to a loop. This is a loop. The only thing I haven't really covered for the loop is how rotation is generated. The takeoff is still just Newton's third law, and the rest is just the same as in the Lutz and in the Axel. So now then, how is rotation generated in a loop? Well, for the loop, the main part responsible for rotation is the shoulders. The shoulders start to rotate, causing you to rotate too, and there you go, you've generated rotation. That's really all there is to it, so this concludes our video. Hopefully you've enjoyed it, and I hope you now understand more about jumps in figure skating.